Welcome to day 7. You can be putting that in your planners. Like usual on videos, we're going to pause for a couple of minutes for you to check your homework answers, and then we'll pause on each of the slides, and you can tell the sub to pause as needed in order to check the work. So we'll pause here for 2 minutes for you to check each of your answers. So there's your matching ones. So you could sub the bottom number in for n to get where the first term should be, the second number in for n to see what the second term, and that should narrow it down enough to figure them out. The alternating ones should have been A and D, those because they're bouncing back and forth, so that helped you narrow it down as well. Again, as we're going through these, if you need the sub to pause on any of them, just yell pause, and then let the sub know when they can hit play again. So on 17, I would say a couple ways to think of it. If you did your limit as n approaches infinity, you're going to get infinity over infinity, so do a L'Hopital's. And then when you neaten it up, you get n plus 1. So as n goes to infinity, that's going to infinity. So our terms are not going to 0, so that automatically diverges by the nth term test. Another way you could think of that, we saw in Unit 6 that any power thing is going to grow quicker than a natural log. Well, on top, it's really like we have to the first. So that's going to grow quicker than your natural log function, meaning it's not going to get smaller each term. So probably the most common way here is to say it diverges by the nth term test because the terms are heading to 0. But if you subbed in each of your numbers and evaluated them, it actually ends up as alternating between negative ones and ones. So you could also say that it diverges because it's a p series and p absolute value is p is not less than 1. All right, so we want our next term to be below 0.001 because in an alternating series test, the next term is the upper bound of your error. So put in the calculator on a graph page 1 over parentheses x plus 1 factorial. Look in the table to find the first one that's below 0.001. Remember, be careful of when they switch to scientific notation. And you can look down at the bottom of the table because it really only shows you a few decimal places in the table itself. So when you're highlighting the box, look on the bottom of the table to see what's there. And when x in the calculator, or really in our problem n was 6, that was the first time we were below 0.001. But notice this one started with n equals 0. So if we're ending with n equals 6, technically that's 7 terms for it to have an error less than 0.001. And then do that summation, and we get 0.368. So basically what we've determined is we know 0.368 is within 0.001 of the infinite sum. Similar idea for each of these, but these ones, the n was equal to 1 on the bottom. So whatever we got for n in the calculator, it was just that for our number of terms. All right, moving to our notes packets. Today's topic is absolute and conditional convergence. So we say that a series is absolutely convergent if the absolute value of that series converges. We say it is conditionally convergent if the original series converges, but the absolute value series diverges. Now, if the original series doesn't converge, well, then the whole thing is just divergent. So let's look at an example. This is most commonly looked at when you have an alternating series, because the absolute value part of it will switch the negatives to positives. So that's usually where it comes up. So we've got this series here. Let's see if we can apply the alternating series test. Is each successive term less than the one before it? Well, based on our few terms written out, it looks like that should be good. As n goes to infinity, will our individual terms approach 0? Well, the bottom will get huge, the top will stay as 1, so that, yes, that is true. So we can say that this converges by the alternating series test. Well, now let's look at the absolute value of that. So we have the same thing, but without any of the negatives. So really, the series that we're looking at is the same as 1 over n. Well, this we've seen several times. This diverges, and we can say one of two things. It diverges since it is harmonic. So that's one explanation you can have. Or this is a p series where p is 1. So, or we could say it diverges because it's a p series with our p greater than 0, but less than or equal to 1. If p is bigger than 1, that's when it will converge. So because the original converged, but the absolute value of the series diverged, we would say that this original series is conditionally convergent. So moving down to the second example, notice they don't give us the formula for the summation, they just give us 4 of the terms. Well, one thing to notice is it's alternating. So we're definitely going to have a negative 1. The first term is positive. So we need to make sure in our exponent when we sub in 1, it comes back as positive. So we could do something like an n plus 1. Then all the numerators are 2, so we can just do times 2. And our denominators are 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. So our denominator we can just say is 3 to the n. Well, if we want to know if it's absolutely or conditionally convergent, or it could be divergent also, let's, because we have an alternating series, see if we can apply the alternating series test. So if we look at our couple terms, it does appear like each successive term is smaller than the one before it. We're really looking at 2 over 3 to the n. Because remember, when we look at the limit, we don't worry about the negative signs, just the absolute value of those terms, the an's. And that denominator will get huge. Numerator stays as 2, so that will approach 0. So we can say that this series converges by the alternating series test. So we now want to take the absolute value of that series. So we'll start out by just rewriting what we had there. And that's really saying that without the negative 1. Well, 2 over 3 to the n can also be written as 2 times 1/3 to the n, since 1 to any power is 1. And notice we have our individual terms there. Now the advantage of writing it as 2 times 1/3 to the n is hopefully it's easier to recognize that that is just a geometric sequence. Notice our absolute value of r is less than 1, so that would lead us to know that this converges. So we'll say converges since it's geometric with the absolute value of r being less than 1. So if the original converged, if the absolute value converged, then we would say our original series is absolutely convergent. All right, same directions. Let's see if this one is absolutely convergent, conditionally convergent, or could be divergent as well. Well, if we look at our individual terms, numerator staying the same, denominator is becoming larger, so it does appear that each successive term is becoming smaller. If we take our ANs as n goes to infinity, that denominator is getting bigger, top is staying as 1, so that will approach 0. So we can say that this converges by the alternating series test. Well, let's look at the absolute value. So really, we're looking at the series of n equals 1 to infinity of 1 over natural log of n plus 1. If we look down on the bottom of the page, we could compare that to our series from 1 to infinity of 1 over n. And there's a graph comparing them. The 1 over n's the open circles, the 1 over natural log of natural log of n plus 1 is above it. So notice that 1 over natural log of n plus 1 is going to always be greater than or equal to 1 over n. Well, something we know that's true, we know that we can say since natural log of n equals 1 to infinity of 1 over n, that's something we saw in a previous one, diverges since, and you have two reasons we can say it diverges again. We could either say since it is harmonic, or you could say that it's a p-series where p is greater than 0 or less than or equal to 1. Now, you don't have to say both those things. You just have to say diverges since it's harmonic, or say diverges p-series where p is greater than 0, less than or equal to 1, but you wouldn't have to on your paper write both those. So, since that diverges, anything bigger than it will also diverge. So we can say by the direct comparison test, our series n equals 1 to infinity of 1 over natural log of n plus 1 diverges. Now you might think, well, why would we think to compare it to the 1 over n? Where would we get that from? Well, remember, natural logs get big very slowly. So if they get big very slowly, 1 over natural log is staying reasonably large. So a 1 over n is going to get bigger faster, so 1 over n is going to stay smaller. And then because that's something that we commonly use to compare, because it's a really easy one, that's what would maybe lead you to use that. So since the absolute value diverges, we can go back up to the top of the page, and our original series, we would say, is conditionally convergent. And these types of problems are somewhat popular on the free response of the AP exam. So one last page in the notes we'll look at. So we've got another series here. We've got the alternating series, negative 1 to the n over radical n. So since the numerator is staying as 1, denominator is getting bigger, each successive term is smaller than the one before. And our denominator is blowing up, top is staying as 1, so the terms will go to 0. So we'll say that this converges by the alternating series test. So let's look at the absolute value of this. So this is really series n equals 1 to infinity of 1 over square root of n. Well, square root of n is really n to the 1/2. So we want to recognize that as a p-series. Our p-value is between 0, greater than 0, but less than or equal to 1. So that would lead us to know it diverges. So we could say this diverges by p-series, where p is greater than 0, but less than or equal to 1. So therefore, the original series is going to be conditionally convergent. All right, so this last one we're going to look at, we've got an alternating with an n factorial over 2 to the n. We've got some of our terms written out. And if you notice, those absolute values of each of the terms, you got a half, 3/4, now 3/2. Those terms are not getting smaller. So you can look at either of our alternating series initial conditions there, but our limit of n factorial over 2 to the n as n goes to infinity, that is not going to be 0. The bottom is just multiplying by a bunch of 2's. Well, pretty quickly in the numerator, you're multiplying by things bigger than 2. So that's going to make the numerator blow up a lot quicker. So therefore, we would say that this diverges by the nth term test. So we would say the overall series is divergent. So the majority of ones end up as conditionally convergent or absolutely convergent. And part of that reason is because that forces you to have to do a little bit more work and show a little bit more knowledge about series. But there could be some cases where that original one is divergent. That's it for this video. Any time remaining in the period, you can begin your homework. Have a great rest of your day.